Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science teaching videos. And today we're going to go back and do a little bit of GCSE science, not just physics, GCSE combined science. We're still going to stay in physics though. And we're going to have a look at the energy topic and work done. Now this lesson is probably not going to be as long as my gravitational fields monster that I put out last week. It's going to be a slightly shorter lesson where we're going to look at what work done is, how you calculate it mathematically, and do a little bit of worked example for it as well, and maybe we can have a little bit of a modelling or an experiment or a demonstration to go along with it as well. We will see how we go. Now, this isn't a lesson that's been asked for by the comments. This is a lesson that I am doing because I'm teaching it to one of my classes at a school I'm working at. Now, that's not to say that I'm talking to them right now, because they're not going to see the same introduction you do. But the assumptions I'm making about the material they've been taught, and thus the material I expect you to know, is going to be based on what they've done rather than the exact order of the specification. So if you feel like, wait, why are you assuming we know this? It's because I'm talking to them who are going to watch the same clips that you're going to watch. I hope that makes sense. I apologise if I lose anybody along the way. But hopefully this will all make sense, all flow together. And in our following lesson, we are going to do this as a double lesson. So this video is one lesson, and then my next video, which I'm hoping to get out this week, maybe next week, will be the second part where we'll look at kinetic energy, one of the most important formulas in all of GCSE science. So without further ado, let's get started. We're going to recap a little bit from the energy topic, and then we're going to dive in, take a look at work done, and see how we make that work. Let's go. So the first little topic, the first little starter activity I'd like us to cover, just to make sure we're all on the same page before we get started, is on what we call efficiency, which hopefully you'll have seen quite recently. Now, efficiency is a formula that comes up a lot in the energy topic, and it's a very common mistake that people make when it comes to working it out and defining what it actually is. So we're going to ask first what the formula for it is, as a quick little recap, and then we're going to do a little experiment, which is kind of a vague application of efficiency, kind of same idea, so that you can see how it works and why it has to be the way it is. So, excuse me, first challenge. First little activity for you to do, either in a Word document or on paper, whichever you prefer. If you've got some notes, look back through those. Can you give me the formula for efficiency? You've got 2 minutes. Pause the video, have a go. What is the formula for efficiency? If you need to look back in your notes, you can do that. But what is it? 2 minutes, pause, go. Good luck. Okay, hopefully you paused the video and now you're back and we're ready to go through the solution. Well, what is the solution? In fact, I'll give it to you first and then we'll talk about it. So, you needed to do, for your answer, a division. And you needed 2 different variables that you will hopefully come across before. That being the total energy and also the idea of something called useful energy. So your solution, in this case, the answer I was looking for, you might have written it as a divide sign rather than a slash or a slash. I've done it like this, is that. The formula for efficiency is the useful energy out divided by the total energy put into a system. So that's your answer. Write it down if you haven't got it anywhere in your notes already, because either you'll have used it before or you will see it again later, and you definitely need to be able to use it. So, what does this actually mean? Well, let's do a little experiment and I'll show you exactly what I mean. So, I have over here a bouncy ball. I have a lot of these, I do like a bouncy ball. And if I was, for the sake of argument, to hold this bouncy ball out in front of me and drop it, it's going to bounce. I think we all know that a bouncy ball bounces, it's right there in the name. But is it going to bounce all the way back up? So I'm going to hold this right in front of my eye line. So actually, I'll leave it top of the screen and let it go. And I just hit the microphone with it. Well done, me. So you might have just been able to see before it went and bounced away. I'll do it one more time with a different ball. So drop. As you can see, it doesn't bounce anywhere near as high as, so it started at the top of the screen, and then I dropped it and it bounced, and it came back up to about there, near the bottom of the screen, because the bounce wasn't 100% efficient. If it was fully efficient, then it would have started there, bounced, and come back up to the same height. And all energy transfers are at least somewhat inefficient. So of the total energy they put in, which in this case would have been the gravitational potential energy, which is something you'd meet later in the topic, when that energy is transferred, there's a transfer to kinetic energy as it falls, as it moves. It then hits the ground, and there's a transfer there, and then it comes back up again, and its kinetic energy is transferred back into gravitational potential. But some of that gravitational potential it had to start with isn't there anymore, because it's been transferred into what we call wasted energy, so that it doesn't have as much left over for the ball. Another very famous example, kettle. So if you're boiling a kettle, you give it the energy from your mains electricity, or from heating it up in some way. Maybe you've got it on the hob, or you use a heating pan. I don't know really how you do it. However you do it, it's usually electric these days. And that energy is then transferred into the kettle as a... Okay, mine doesn't have a heating coil that I can show you. Boo. But there's normally a heating element in there which then heats up, and then that heats the water. But not all the energy that comes out of your plug goes into the water as heat. Some of it is transferred into useless or wasted energy stores. For example, you might have some of the electricity being used to turn a fancy light on your kettle. Mine does that. Or you might have it being transferred as sound into your ear, so you can hear the kettle boiling, but that's not being used to heat the water. The energy transfer is inefficient somewhat, and you can then work out how inefficient by knowing the total energy you put in, so its initial gravitational potential energy, what energy it had left at the end that was useful, the gravitational potential energy on the bounce, because that's the energy we want it to bounce as high as possible, and then use that to work out the efficiency of the system. So let's say it started up here at 1 meter high, and then it bounced and it came back up to 50 centimeters high. Then the efficiency would be 0.5 meters divided by 1 meter, or energy at 1 meter and energy at 0.5 meters. That one over that one gives you the efficiency. You can then times that by 100 and you get that as a percentage. We'll do another calculation like that later on in the video. Just wanted to make sure that everyone had the idea. So with that all done, I'll get off the screen now and we'll have a talk about work done. So let's have a talk about work done. What is it? How does it work? Pun very much intended. And how do we calculate it? So the first thing I'm going to say about work done is it has units of energy. You should already know what the units of energy are, but I will tell you. Joules. Energy is measured in joules. You should really know that by now. However, quite often in the energy topic, we talk a lot about things called energy stores. If you're of a slightly older ilk, or you talk to certain people who are older than you might have heard of energy types, which are different forms that energy can take. We don't really use that terminology now. We talk about energy stores, and work done is not one of these. What it is instead is an energy transfer. And no, that's got nothing to do with the football. So what I mean by that sentence, you can read it, and obviously this will also be available if you've got access to my slides, is that you don't see energy stored at the end of a process as work done. So let's say, for example, I wanted to imagine that this is up rather than crossways. I wanted to lift up my pen and move it across the screen. I have to do work, and I'll talk about how we calculate this in a minute. I have to do work to move it across the page, across the board, or upwards, or whichever direction you like. I have to do some work, and I'll calculate how much that is. But the energy is not stored as work done. Once the object has stopped moving, or there is no force being applied on it to make it move, then the energy is transferred into a different energy store, an actual energy store. And we'll talk about the two main ones in a moment. But with regards to the pen, if I was to lift it up, it will be transferred as work done into kinetic energy, into the kinetic store. And then once it got to a certain height, or once it was started being moved upwards, it would be transferred again into the gravitational energy store. Gravitational potential energy is something that we haven't met yet. So, whilst I'm going to talk about it as a sort of type of energy, be very clear, it's not an energy store. So if you were ever asked, can you name me 3 stores of energy or 3 energy stores, you cannot say work done. Because work done is sort of the intermediary step, as opposed to, say, kinetic, which is what we're going to do in the next lesson, and what is which is an energy store. I'll get my English right in a moment. So, work done is to do with making objects move or stop. I'll put in brackets, because you do see questions, for example, where you have work being done by brakes, for example, to make something stop moving, but generally it's to do with moving objects. It's the energy transferred by moving an object. So, if I was to write a definition, so you should be making notes as you go, I'll write a little definition here. Work done, I'm going to define as the energy transferred by moving or stopping an object. So put that in a box, just draw a box around it, something like that, because that's the important bit. That's the important definition that I'd like you to take away about what work done is. Now, it's not comprehensive, because you might say, well, once the object started moving, is it still transferring work? Well, it depends on the object, but it's the energy transferred by moving. It's not the energy stored, again, come back to this point, it's not the energy stored when an object moves or is moving, it's the energy transferred by making it move or making it stop moving. So I'll leave this on the screen for a second to let you take some notes down, pause the video if you have to, and then we'll talk about how we actually calculate our work done. Okay, should have paused the video. I'm going to clear this in 3, 2, 1. Let's clear it. So, how do we calculate work done? Well, quite simply, actually. So, if you're going to move an object, work done equals. If you're going to move an object, then you've got 2 factors involved in the amount of energy you need to make it move. The first is to do with how far you want the object to move. So more energy would be transferred in pushing my pen all the way across the board than in moving it halfway across the board. Or, for example, it might take more energy to throw the bouncy ball across the street than it would to lift it into my hand. The distance moved matters. I'm going to write that over there. And we multiply that by how much force it took to move the object in the first place. So that's the shorthand version. So the work done, so if we want this in a sentence form, the work done to move an object is equal to the force applied to the object multiplied by the distance moved. And I'm going to put in brackets here while the force is being applied. Now I put that in brackets because it's less important, but it's also worth noting. So for example, if I was to push my pen across the board, so I give it a push, off it goes. If I'm pushing it the whole time, then I'm applying the force across the whole length of my board. If I just push it a bit, then I'm only applying that force over, say, that much distance. That's the only distance over which I applied the force, but the object has ended up over here. So you take that distance, i.e. the distance over which the force was applied, and multiply it by the force that you applied. If you want that in a symbol form, you would have that as work done, which you may also write as W, but I'm going to write as WD so you don't get it mixed up with weight. As you go forward, is force multiplied by, and you've got two options for your symbol here. Now I'm going to write this as a lowercase d for distance. However, as you get particularly higher up in GCSE physics and GCSE science in general, you will often see D swapped for an S, or certainly I've seen it swapped for an S. So I'm going to write D here, but if you see S on tests or on past paper questions, do not be alarmed. It's the same thing. I'm just using a different symbol, or I'm using the other option symbol. And we also write this in the form of an equation triangle. You'll get used to seeing these across a lot of the lessons I do in this topic. So an equation triangle is a way of showing you what you have to do when it comes to your equation. And this one fills out like this. Work done equals force multiplied by distance. So what this does is allows you to calculate any of the three variables in a split second. So let's say I want to calculate the work done. Okay, so I'm going to put my hand over work done, and it tells me I have to do force times distance. Let's say I want to work out the force. Okay, I'll cover up force. So I have to do work done over distance, aka work done divided by distance. Want to work out the distance? Same idea. Work done over the force. Work done divided by the force. You'll get used to seeing that, and we'll use it a bit later, but I wanted to introduce you to that. So definitely this, that, and that. So the word equation, the symbol equation, and the triangle, I need you to get them down. I absolutely need you to take those down before you move on with the video. So I'll give you a chance to do that while you pause. And the only other thing to show you then is the unit. I'm going to actually leave the boxes up while I remove the definition, because you'll hopefully have a chance to write it if you are writing it. And that means we need to now talk about units. Now, I'm one of those people who is very, very pedantic and very, very picky about units. So you need to make sure you know your units and know how to manipulate them in the right way. So the unit of work, I already told you earlier. It's a type of energy. It's an energy transfer. Therefore, we measure it in joules, or capital J. When it comes to the force, most of you will already know this. It is measured in newtons, or capital N. And the distance is one that can cause a few headaches, because it's very common for questions to be written with the distance being in centimeters or millimeters or kilometers. Why do we not say kilometers more? Whatever. So the distance that you're going to need to convert into always is in meters, lowercase m. Those are the 3 units. If you see a question, and you'll see one of these later on, where it gives the distance in, shall we say, kilometers, or the force in kilonewtons, or the work done in millijoules, you have to be able to convert and get back into these normal units. So you might have to go 1 kilonewton equals 1,000 newtons, because the K symbolizes 1,000. You might have it as 1 centimeter, which is 0.01 meters. Or you might have it, I've also seen this, 1 megajoule. It's 1,000,000 joules. 1 million joules. There's just a few. You will see more. You need to get used to switching between them. You'll get some practice a little bit later, but that's the key thing. So that's pretty much the core points of what you need to know. This bit, this bit, this bit, that bit, that's just a little bit of a useful aside. Now let's work through an example together, and then I will set you off on your main task. Right, so I'm going to do a worked example here just to show you how we do this sort of thing. So if I have a force of 25 newtons is applied to push a box a distance of 4 meters. What is the work done? If you want to have a go at this yourself at home, pause the video now and give yourself a couple of minutes to have a go. But I'm now going to go through the solution for you, just as a worked example. So, you need to take this formula that we've got at the top. WD is F multiplied by D. And then we need to start plugging in some numbers. So, I know my force, F, equals 25 newtons. And I know my distance equals 4 meters. If I then need to plug them into here, so my work done equals 25 newtons times 4 meters equals 100. I'll stick this in my calculator just so you know I'm not doing some space magic. 25 times 4, just in case you didn't know off the top of your head. 100. And then what's the unit I need to put it in? I need to put it in joules. Now, obviously, if this had been 400 centimeters, then I'd have had to convert that into proper meters. Or if that had been in kilonewtons, I'd have had to convert that as well. That was just a nice, simple, worked example. And this sort of work that you see here is pretty much a 3-mark question done for a GCSE exam. Certainly 2, maybe 3, depending on maybe what tier you're at. That is the broad basics of what you need to do. So, coming up on the screen in a moment, and also if you've got access to them in the Word document that I've got, then there's going to be a series of questions for you to have a go at involving work done. So, you're going to have a little bit of practice at calculating work done, rearranging the equation, using the different units as well. You're going to have a bit of time to practice that. I'm going to give you about 10 minutes to have a go at as many as you can. When you are done, you can come back to this video. So pause it now and then come back to the video in about 10 minutes or when you're finished and we'll work through the solutions together. Good luck. Off you go. All right, let's go through the answers to the little sheet that I have asked for you to do. I hope that you were able to get on with it all right. It wasn't too overly arduous. There was a little bit of everything there with some rearranging and some conversions. So, well, let's see how we got on, shall we? So, question 1, you had a force of 50 newtons being moved a horizontal distance of 30 meters. Now I'm writing in shorthand, and this is enough. This should be a full mark answer that I'm going to write down. If you wrote longer form than this because you weren't able to print off the work, then that's absolutely fine, probably for the best. But I'm going to give you the abridged, like, full mark answer here. It then asks you to find out the work done. So the work done, I've written my triangle up in the corner. I cover over the work, and it tells me I have to do the force times the distance. Times D equals 50 newtons times 30 meters equals, let's take that in our group calculator, 50 by 30 gives us, not that, 1,500. And remember, you have to give the unit as well, which is in joules. So if you treat that like a 3-mark exam question, then you would get 1 mark here, 1 mark here, and 1 mark here. Or you would be given that it was in joules, and your third part would be for this. It would be either or. It depends quite on how this question is put together, whether you're asked to give the unit or not, determines where that third mark would come from. But that is the full worked answer, 1,500 joules. Now, the second question is where things got a little bit more complicated. So this time, question 2, you had a force of 200 newtons and the distance was 50 centimeters. Now, you might think, okay, so I just need to use that formula, do 200 times 50 and I'm good, right? Not quite. Easy mistake to make, and I understand if you did do it, but you need to notice your distance at the moment is in centimeters, and that needs to therefore be changed into meters. So if you're going centimeters to meters, if you look at a meter ruler, if you had one on a hand or a tape measure, you would see that there are 100 centimeters in a meter. So we need to divide this number by 100 to get 0.5 meters. That's really, really important, and it's why you've got to read your units very, very carefully. So it says it's in centimeters, you need to get it into meters. From there, the question proceeds in the same way. Work done equals force multiplied by distance equals 200 multiplied by 0.5 equals 100 joules. You see the difference? If that had been 50, this would have been 10,000, which is a huge amount of energy but he's basically pushing 20 kilograms that far-ish, maybe a bit further than that. It's not that far at all. So you have to remember about this unit conversion. And this probably would be a mark in and of itself. If you didn't do the conversion but did the right thing, you would have lost 1 mark. So there's a mark, there's a mark, and there's a mark, if you like, if each of these are out of 3. Now, question 3, spice things up again in a slightly different way. What did we have this time? So question 3, you were given that you had a work of 5,000 joules, and you were also told that it was over a distance of 100 meters. You were then asked to calculate the force applied. And for this, we need to go back to our equation triangle. So let's cover over the force, which is the usual thing we do with this. You can see I've got to do W, or work, divided by D, the distance. So W divided by D equals 5,000 divided by 100 equals, if I'm right, we'll stick that in together, 5,000 over 100 is 50. But, of course, we still need to give the unit, and the unit, because we've got a force, is in newtons. So you'll get 1 mark for rearranging the equation, 1 mark for plugging the numbers in, and then 1 mark for the final answer. You may have a 4th mark if it's asking for it in newtons, but or if you were not given the unit to put it in, you might be asked and get a 4th mark for writing newtons, but that's the basic structure of that question. And question 4 is where we start to put it all together, with any luck. So, we have here a force of 200 newtons again. And this time we have a work done of 8 kilojoules. So, because we've got that K, we know we're dealing with kilojoules. Same as grams and kilograms, that kilo symbolizes 1,000. So, you have a total work of 8,000 joules. And then it asks you to calculate how far the toe, or the distance, was. So, we go back to the triangle, cover it up, and you see I have work done, and it's over the force, so it's divided by the force, which is going to be 8,000 divided by 200, which is, let's stick that in the calculator one more time, 8,000 divided by 200 is 40. And of course, we're working with a distance. We've got joules, we've got newtons. Remember what the unit of distance was earlier. Might think, oh, is it in kilometers? Is it in miles? Is it in whatever? Because we've got joules and newtons already, the answer is in meters. Now, if you'd have done 8 over 200, you'd have got 0.04, I think. 0.04. And if you'd have given the answer as 0.04 kilometers, I'm going to write this in brackets. So if you did 0.04, but you got your answering and wrote kilometers, that is also correct. But generally, we look to get it into meters, so your answer will be 40 meters. So those are the solutions. Each of them is out of 3. So for your marks here, you have 1, 2, and 3. Actually, we'll make this one out of 4. Because you've got the conversion as well. So 1, 2, 3, 4. Make that one out of 4. So your total score should be out of 13. Add them up, see what you got. Hopefully you did all right. And we will do a proper little test where appropriate, so you can I can see your understanding of it going forward. But we will come to that when we come to that. For now, I want to talk about one more thing before we get on to our last little bit of the lesson. So this is our last bit of teaching before we get to the end of the lesson. And that is going to sound a little bit obnoxious, but I'm going to call it the fate of work done. Now, that might sound utterly pretentious to you, and I don't blame you, but what I mean by that is we said that work done is a transfer. You might remember that from earlier in the lesson. Work done is a transfer. So what store or stores does it transfer to? So if work done transfers energy from one store to another, so it might be that you had it just sat on the floor with a little bit of energy and you pushed it. What would that work transfer end up as? What type of energy and what energy store would you usually end up with as your final stores for the system? Well, there's about 2 or 3 places it can end up. Now, the obvious one you should be able to get just from watching me apply some work to this rubber. Do it again. So, what is the obvious energy store for that work done? If I've done some work by pushing the rubber, what energy store have I clearly transferred to, perhaps most obviously? Well, the object is moving. The object is now moving, and there is one type of energy store associated with the motion of an object and how fast that object is moving. And that is the topic of our next lesson, on our next video, kinetic energy. And this one is our useful energy store. Generally, if we're applying a force to an object, we want that object to move. If we're doing work on an object, we want it to move, and so we want it to gain kinetic energy. We want energy to be transferred to the kinetic energy store. The chemical energy in our muscles is transferred via the means of work done into the kinetic energy of the object, if you like. There's a lot of bits and bobs that go into that, but that's our useful energy store. But you might be able to note this one a little bit more clearly if I push my tape measure. I'm going to put it that way up. The other energy area that you could end up with is a bit of a broader scope, and one you'll be able to have hopefully picked up just from listening. So this one, I'm going to say the other place that it can end up is dissipated into surroundings. And when that happens, you end up with heat, and I'm going to put in brackets sound. Now, sound is not typically regarded as an energy store in particular, but obviously you can hear when you move something, you might hear the sound, and so clearly there's some energy being transferred to make the particles in the air vibrate and travel, cause the sound to travel to your ear. So clearly some energy has been transferred via the medium of sound, if you like. It's sort of a bit of a dodgy term, but it's not really an energy store again. So I'm going to put it, but the main one you're looking for is heat. And you'll know that from friction. If you rub your hands together for any length of time, you'll feel that they start to get warm. And that's because the work you're doing, some of it is being transferred into the kinetic energy of your hand as you slide it along your hand, but some of it is being dissipated and transferred into the heating of your hands via friction. And this dissipation into the surroundings is our wasted energy. So as a rule of thumb, if you were ever asked, when work is done, what's the wasted energy? Your go-to answer will probably end up being heat. Now, if you can see another energy store going on, so for example, you might have one where you want work to transfer to kinetic energy, but it ends up that it's sort of being pushed up a hill. So some of it's being transferred to gravitational energy as well. They're both kind of useful. There's a little bit more to it than that in certain systems, but generally you've got kinetic energy and heat. But one caveat, I know I keep saying this as bits and bobs. So bear in mind, what if the object was already moving? I'm going to pose this as a question. I want you to answer for yourselves first. What if an object is already moving? So let's think about that example in one of the questions where we put the brakes on. We already have kinetic energy as our store that we started with, and we're transferring via work out of that store. Where do we want it to end up then? Well, in the end, you want it to end up as heat, because you want the car or whatever is being stopped to stop. And the general way you stop it is through the application of force and doing work on it. And if it's through brakes, generally you'll end up with heat being transferred to the surroundings. So sometimes you want to get rid of that kinetic energy and transfer it to another store, which will usually be heat, because you're trying to stop. But generally, there is your sort of summary answer. But last thing then for today. Last thing of all, and then I will let you go and get on with the rest of your day, because you're no doubt absolutely fed up with the sound of my voice by now. So our final plenary activity, just to check our understanding, is as follows. It's a two-part question. Here's the first part, and then you'll have a go at the second part once you've done this. So I have here a question. A crane applies 75 kilonewtons of force to lift a pile of bricks by 400 meters. What I want you to do as your little task, and write this question out, put it at the bottom of whatever you've been writing on throughout this lesson, is to tell me what the work done on the bricks is. As a bonus challenge, if you can think back to earlier in the video, what's the work done in megajoules? Give yourselves 4 minutes to have a go at this. Pause the video, then come back and we'll have a go at solving it. All right, let's see what the answer is. So, first off, we need to work out what we've got. So we have work done is desired, and we know that from this lesson as force times distance. I know my force is 75 kilonewtons, and my distance is 400 meters. Now, you might think, okay, that's easy. 75 times 40, done, great. Or 75 times 400, sorry. Not quite. Remember, got kilonewtons here. So that means that our work done is going to be 75,000, because you've got that kilo, multiplied by 400, gives you, already done it here, 3, and then 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 joules. And if you might remember from the start of the video, those who did try this, in megajoules, remember that 1 megajoule is 1 million joules. So 30 megajoules. Okay, so that's the solution to that. 30 megajoules or 30 million joules, depending on how you worked it out. The second part, I'll leave that there for you to write your answer. The second part this is coming back to what we did right at the start of the lesson to see if you can remember, just sort of a bonus little challenge question. If the bricks only gain 20 megajoules of GPE, which is gravitational potential energy, when lifted, what is the efficiency? So this again comes back to what we did right at the start, just to see if you can remember. Again, give yourself 3 minutes, have a go at this. Might not even need that long. So 3 minutes. You need to go back to the start of the video, at the start of your notes, do so. See how you go on. Okay, let's go through it. So, right at the start, I said that the EFF equals useful out over total in. Now, the useful energy out, because remember, we're lifting the bricks. We want them to get as high as they can. So we want them to have as much GPE as possible. So 20 million, or just 20, over the total energy that was put in. That's the work done that you calculated in the previous part, which is 30 million. That's going to cancel and that's going to cancel because you're just dividing by a million on both of them. 20 over 30, those also cancel, is 2/3, also known as 0.67. You can check that for yourself, or if you prefer it as a percentage, 67%. And that's it. That is everything that I think you need to know about work done. And we've also had a quick look and recap about efficiency as well. And there we go. That is everything that I wanted to do today, all about work done, a little bit of energy conservation and efficiency thrown in for good measure. I do hope you've enjoyed today's lesson. I do hope you found it useful and entertaining in some way. I know it's been a slight change of format from the normal tutorialis videos I've done in the past, where it's just been the whiteboard. There's been no experimentation or anything like that. Do let me know your thoughts on the format in the comments below. I always like to know what you have to say. Obviously, this was not a lesson that was asked for by the comments, and there'll be more lessons like this going forward. So our next lesson will be on kinetic energy. I'm afraid you're going to have to sit through a little bit more GCSE science if you are more of an A-level minded person. but that is what we're going to do. I've had requested from the comments to do something involving gas laws, so I'm probably going to make a double lesson out of that, one for GCSE students, one for A-level students going forward. And of course, if you have any suggestions or requests, do let me know via the comments, or if you're still here from the Premiere chat, then you can ask me there as well. I definitely want to know about what you'd like me to teach so that I can blend the two together with what I'm learning about and teaching myself versus what you guys want to know. I can blend the two together and make a proper job of it. So let me know in the comments below, and thank you very much for your time and for your hard work. I'm sure you put plenty in. As I say, next lesson will be kinetic energy, whenever that so happens to be. But for now, this has been Tactica Imperialis, and this has been all about work done for GCSE Combined Science. Thank you very much for watching, and I'll see you all again. Bye for now.